and welcome to another episode of Night Sky News for October 2022 with me, astrophysicist Dr. Becky Smethurst. This is the show where we chat about what you should look out for in the night sky in the next couple of weeks, and we chat about what's been happening in space news in the past few weeks. Any research papers I mention are all going to be linked in the video description down below if you'd like to read them yourself. And we've also got chapters linked down here if you'd like to skip ahead to any specific news story. Because real quick, just before we dive into everything, I just want to remind all of you in the US that my new book, A Brief History of Black Holes, is out in hardback versions and in stores on November 1st. It's already out in audiobook versions and ebook versions online if you can't wait until then. Plus, if you're in the UK or the US, the podcast I host for the Royal Astronomical Society, the supermassive podcast, all of us that host it have put together a book celebrating the year in space that was 2022, which is out on the 27th of October. There's an Ask Dr. Becky section in the book, so if you've ever sent in a question to the show that hasn't been answered, it might have been answered in the book instead. So I'll link both the podcast and the book in the video description down below if you want to check either of those out. But without any further ado, let's kick things off and start by looking up. Now, for the rest of October and throughout the month of November, the planets are going to be spoiling us once again, with Saturn, Jupiter, and Mars all visible in the evening sky, and you don't need a telescope or binoculars to see them. So Jupiter and Saturn will be visible as soon as the sun has set wherever you are in the world, and then will disappear around about midnight, depending on where you are. Mars rises a little bit later in the evening at the minute, and it'll be visible right up until sunrise. Now, Jupiter and Mars are fairly easy to spot. Jupiter because it's just so bright. It's brighter than any star. The only thing brighter than it is the moon in the sky at the minute. So if you're looking south and you can see something that you're like, wow, that's insanely bright, that is Jupiter. And Mars, obviously, it looks just that slightly reddish in colour than any star. So again, it's fairly easy to pick out. It's fairly bright because it's nearby to us. Saturn, however, is obviously a lot further away than either Jupiter or Mars. So it's a bit fainter, and it makes picking it out against all of the background stars just that little bit more difficult. But the moon is going to help out with that, because on the 1st of November, the half moon will be just below Saturn on the sky, hopefully making it just that little bit easier for you to spot. And once you've found it, notice how Mars, Jupiter, and Saturn all make a line in the sky, which is essentially the flat plane of the solar system that we call the ecliptic. Now, if it's clear over a number of nights for you, you'll also notice how the moon moves along that line, skirting past Jupiter on the 4th of November, skirting past the star cluster Pleiades on the 9th of November, and then Mars on the 11th. It'll be fairly near Orion in the evening sky on the 11th of November with Mars, a sight that in the northern hemisphere definitely screams
winter is coming.
Winter is coming. In the middle of all of that, there's also going to be a lunar eclipse in the early hours of the morning on the 8th of November for the Americas, and in the late evening of the 8th of November for Australia, New Zealand, and Eastern Asia. Now, a lunar eclipse is when the moon passes into the Earth's shadow, which, because of the atmosphere, is a little bit fuzzy edged, so you get all these different regions of it. You also get a sunset shadow, where red light is bent more by the atmosphere and hits the moon, turning it this beautiful orangey red colour. So if you're somewhere within this red coloured area on this map, you're going to be able to see the whole of the eclipse. And to the east of here, you'll see the start of it during moon set, and to the west of here towards Asia, you'll see the end of the eclipse during moon rise in the evening. I'll pop a link in the video description below to a website that you can key in your location and find out when and how much of the eclipse will be visible to you. Then all this month, we're going to have meteors or shooting stars from the Leonids meteor shower. Now, this can put on a show every 33 years or so, the last one being in 2001, but in the in-between years, it's not as spectacular. So if you're lucky, in the darkest of skies on the peak of the shower on the nights of the 17th to the 18th of November, you might see 10 meteors an hour or so. So I wouldn't suggest making an occasion of trying to view this meteor shower. Just wanted to flag that in case you do see it maybe overhyped in the media, because it usually is spectacular every 33 years, but not in the in-between years. But if you are out on a clear night in November and you do see a shooting star, a meteor, streaking across the sky from the constellation of Leo, you can be pretty sure that what you've seen is a Leonid. Now, real quick before we get to the space news section of this video, I'm really excited to say a huge thank you to 80,000 Hours for sponsoring this video. So 80,000 Hours is a non-profit that aims to help you find a career that's both fulfilling and makes a big positive difference. Over the last 10 years, they've done a ton of work, including some with academics at Oxford, so some of my colleagues, collating a load of research, evidence, and the best advice to help you find a job that has a huge impact. The name comes from the number of hours in an average career. 40 hours a week, 50 weeks a year for 40 years. Now, as hardworking as I'm sure many school and university careers advice services are, they do have to cover such a broad range that the advice is usually very generic, covering a lot of the mainstream careers like doctor, lawyer, or accountant. Or in my case at school, after I did the career aptitude test at 16, I got dog walker. The irony being that I was scared of dogs at the time. But thankfully those tests and that generic advice are not your only options, and that's where 80,000 Hours comes in. They have a website detailing all of their research, plus it also has a job board with hundreds of listings that are based on all of their research that they believe are the jobs that will help you make the world that bit better. And all of this advice, all their research, their evidence, their job postings, it is all free forever. So if you join the newsletter now, you'll get a free copy of their in-depth career guide sent to your inbox. Just sign up at 80,000hours.org/Dr. Becky. So get started planning your career today. And a massive thanks again to 80,000 Hours for sponsoring this video. All right, and now it's time to come back down to Earth and chat about what's been happening in space news in the past month. Alright, you all know what I'm going to say. The big news this month was the DART mission that successfully crashed into the asteroid Dimorphos on Monday, the 26th of September, and 2 weeks later was announced as a success by NASA, with the impact changing the energy of the asteroid enough to reduce its orbit time around the much larger asteroid Didymos by over 30 minutes. I talked through all of this and how we measured this orbit change in my recent video on the DART mission, which I'll link below, and why the change in orbit was 25 times larger than was predicted, and what that means for the, future protection of planet Earth in the case that we ever find a potentially hazardous asteroid. So check that out if you want to know more about that story. I covered it much more thoroughly in that video. Now, moving on to JWST now. And before we get to those beautiful images that were released, we'll get to them, I promise. I want to talk quickly first about how unfortunately there's been no update on the status of one of MIRI's observing modes, which is currently down. So MIRI is one of the 4 instruments on board JWST which records the light the telescope detects. And across those 4 instruments, there's 17 different modes or ways of observing in total. So it's just one of the 17 different ways that we can use the telescope that's down. So it's not a catastrophe, but it's still a concern, right? So the issue is with the medium resolution spectroscopy mode on board MIRI. So one of the modes where you take the light and switch it through a prism and you sort of get that fingerprint of light, that trace of how much light of every wavelength you're receiving. And in that mode, there is what's known as a filter wheel, essentially a wheel that has these filters on that allows you to separate whether you let through the shorter wavelengths of light, the sort of mid-range wavelengths of light, or the longer wavelengths of light that MIRI can detect, and lets you choose between which ones of those that you view. And according to NASA, one of those wheels has increased friction. It's a bit sticky, essentially, right? It's getting stuck as they try and turn it. So that's why the observing mode has sort of been paused since the 6th of September when that was first discovered, and a review board was convened to try and figure out what was going on and what to do about it. NASA then announced there was an issue on the 20th of September, and I made a YouTube short about it at the time if you want to check that out. But since then, there's been no official update, although I have spoken to a couple of my colleagues that are on the MIRI science team, and they are very hopeful that observations will resume soon in that mode. But until then, if you're someone that's been awarded time to use that mode with MIRI to do your science, you really do just have to be patient for now. But I'm going to be keeping my eye on the published observing schedules that are posted online. I'll put a link in the video description if you want to keep an eye on them yourself as well, just to see if any, observing tests with the MRS mode on MIRI pop up in the next few weeks. But, the other 16 modes on JWST are all still working beautifully. This month we actually had the release of the image that I have been waiting for. It was actually sort of the target that I had my money on as being one of the very first images that were released, those big 5 that were released back in July. But no, they made me wait just that little bit longer to see the pillars of creation in all of their glory. Honestly, the detail on this image is like nothing I've ever seen before. If you do anything today, download the full resolution image, which is huge, and just zoom and pan around. It's honestly extraordinary. So the pillars of creation are part of the much larger Eagle Nebula, a huge cloud of gas and dust where new stars are forming about 7,000 light years away in our galaxy, the Milky Way. If you want to try and spot it yourself, it's just north of the constellation of Sagittarius. The further south you are, the higher above the horizon this will be in the early evening sky. If you're sort of in the UK or Northern Europe, we've got no chance at this time of year. It doesn't even rise above the horizon for us. Each pillar is about 4 or 5 light years long, i.e. it takes light, traveling at almost 300,000 kilometers a second, 4 years to go from one end of a pillar to the other. And it's worth just noting here that every single point of light that you can see is a star, which JWST has been able to reveal where the Hubble Space Telescope couldn't. Stars form in these very dusty areas. Dust we know can act as a catalyst to essentially kickstart fusion, but it also blocks visible light. The dust is around about the same size as the wavelength of the light, so it just gets scattered. And so it's opaque to us when we look, with our eyes, or with a telescope like HST, the Hubble Space Telescope, when we look in visible light. But JWST, which sees in the infrared, which is much longer wavelength of light, can easily go around that dust and essentially pierce through it, allowing us to see the stars that are forming inside of this nebula. Now, once again, because this image is made of infrared light that's been detected by JWST, it doesn't have a real color necessarily. So this is a false color image. NASA have added color to it in order for our eyes to be able to pick out more detail than we would necessarily on a black and white image. So you can see that here where it tells you which of the filters that let through a certain range of wavelengths to the telescope have been colored which color. And we stick essentially with the same principle that you would with optical light, in that shorter wavelengths is blue light and longer wavelengths is red light. So here you can see that the shorter wavelengths filters have been colored blue and the longest wavelengths that were detected through another filter have been colored red. But also the wavelength of light that an object is giving out is related to its temperature. So shorter wavelengths are given out by hotter things and longer wavelengths are given out by cooler things. So anything that you see in this image that is bluish in color is hotter and anything red is colder. So you can see the wispy blue gas here off the edges of the nebula. That's gas that's essentially been heated by a newly formed star and then streamed off, causing these wisps. We saw something similar in that cosmic cliffs image that was first released from JWST back in July. Almost it looked in that image like it was boiling off the top of the nebula. You've then also got these red spots on the ends of the pillars, and I saw a lot of people on social media asking about these. This is where the gas and dust is likely the thickest. The energy from, new stars inside is insulated the most, making these cold tips. Almost kind of like how the tips of your fingers get the coldest on a very chilly day. So images like this of the pillars of creation and the cosmic cliffs that we've already seen as well help us to better understand how stars form, especially what happens at some of the earlier stages of star formation, where maybe the star isn't hot enough yet to actually sort of blow off that cocoon of gas and dust JWST allows us to pierce through that and reveal in great detail what we haven't been able to see before. And before we've only been relying on, for example, models and simulations to tell us, what might be happening at that stage. So there is so much more that we still don't know about the very early stages of star formation. So I think there's going to be a lot of astronomers all around the world, probably lots of PhD students as well, looking at these images in great detail, i.e. the images that come from each of the different filters that were all combined to give us this one coloured image, to determine what wavelengths are we detecting in this region? So what temperature does that have? What energies are going on here? So we can sort of, piece together the puzzle of what's going on when stars form and answer the plethora of questions that we still have. Then we had this incredible image taken by MIRI this time. The previous one was from NIRCam. And this revealed the infrared light coming from the glow of the dust itself, much longer wavelengths, around this pair of stars known as Wolf-Rayet 140 or WR140. Now, Wolf-Rayet stars are very massive stars, about 25 times more massive than the sun. And for some reason, we're still not entirely sure why, they lose mass at an incredibly high rate. Essentially, material is streaming off them in what we call a stellar wind. Now, the sun does this too, but at a much lower rate. It has a stellar wind, it also burps up some particles, and when those particles interact with the magnetic field, they get funneled down to the poles, and then we get these spectacular light shows of the aurora. But this system that they've imaged with MIRI is particularly special because it is a binary star system. And what that causes the Wolf-Rayet star to do is to belch up a lot of dust. Now, this happens every 8 years or so, and so you get a shell every time, giving this pattern that's almost like tree ring that allow us, to age them. So with 17 rings here, we know these stars have been throwing up dust like this for at least 130 years. Now, you can only see the edges of the shells in this image in the same way that you can only see the edge of a translucent bubble. The middle appears transparent to you because you're looking through a very thin piece of film, but on the edges, you're looking through more of the soap, and so it's translucent rather than completely transparent. And so in the case of these shells, we have the same thing here. We don't see them as full spherical shells. We just see it where we're looking through the thickest part of the dust in this case, and we just see the edges in these rings. What's particularly exciting about this dust, though, that's been detecting these rings, is that back when that currently paused observing mode on JWST, the medium resolution spectroscopy of MIRI, was actually still up and running, they did use it to observe WR140. And they took the light that dust was emitting, split it through a spectrum, and got that sort of trace of light of each wavelength to get the fingerprint of what the dust was made of. And they found that it contained a lot of polycyclic aromatic hydrocarbons, or PAHs, which is 3 words that get astrochemists very excited, because these molecules, we know that they're very important for the formation of planets, and they contain a lot of carbon, which for carbon-based life forms like us is very helpful. But where it comes from in the universe and how it's made have always been a little bit of a mystery. So it turns out that perhaps it's these Wolf-Rayet stars that could do the making and the mixing and the distribution of all of these very important polycyclic aromatic hydrocarbon molecules. Now, from the infrared of JWST into the very high energy gamma ray light. And this month we saw the detection of the brightest ever gamma ray burst. On the 9th of October 2022, many different gamma ray telescopes detected this burst that lasted 10 minutes with photons with energies twice that's ever produced in the Large Hadron Collider at CERN. It was so energetic that it even disrupted long-wave radio communications. We then had follow-up observations of this gamma ray burst with optical telescopes like the Geminid South Telescope in Chile that suggest the burst came from a galaxy 2.4 billion light years away. So yes, whatever caused this burst actually happened 2.4 billion years ago, and the light has been traveling through the universe to us since then, and we've only just detected it. Now, although that might sound a massive distance, we think this is the closest gamma ray burst that we've ever detected. Because it was so bright, we've been able to follow it up with over 50 different telescopes around the world across multiple different wavelength ranges across the spectrum of light, so we can maximize how much we can learn from this thing, including JWST as well. Remember those observation schedules I mentioned that they published every week before? I couldn't help but notice that MIRI was queued to observe this gamma ray burst very soon, which is very exciting. Because we're still not 100% sure what causes gamma ray bursts. Like, I remember when I was doing my undergrad degree in physics, like back around about the 2010s, there was loads of ideas floating around. No one really knew which one it was. And it wasn't until there was a gamma ray burst detected at the same time as gravitational waves from the merger of two neutron stars that we had any concrete evidence for what could cause them. But there's many different types of gamma ray bursts with lots of different properties. You know, they're classed as short, long, or ultra long bursts as well that have been associated with supernova, sort of when a star runs out of fuel and dies, maybe even hypernova if it's an incredibly massive star, or even the Wolf-Rayet stars that we just heard about. So with this very bright gamma ray burst that was detected that allowed all of these follow-up observations that will hopefully, get analysed in the next couple of months and reported on, and when they do, I'll feed back on this channel as well. And I think everyone's really hoping that we'll learn something about, what are the big cosmic generators of these gamma ray bursts. Now, it could be that gamma ray bursts are generated by what's known as tidal disruption events, or TDEs, which is the focus of this next study I want to talk about from Senders and collaborators. So a TDE, a tidal disruption event, is when a star or a cloud of gas gets too close to a supermassive black hole and gets torn apart by the strong gravitational forces. It gets spaghettified because the force is so much stronger on the side closest to the black hole than the other that it gets stretched out like spaghetti. Now, some of that shredded mass of the star will end up in what's called an accretion disk around the black hole. Essentially a swirling flat disk of gas that will eventually spiral down to become part of the black hole and add to its mass. And if this happens, you can have a very bright burst of light in X-ray, UV, optical light as the gas heats up and starts to glow. But it can also become so dense in that accretion disk with so much material sort of jostling each other, sort of fighting to get down into the black hole, that the pressure increases and increases and increases, so that the only thing that accretion disk can do is alleviate that pressure somehow, almost with a sort of burp of material back outwards after this big glut. We usually call that an outflow or a wind from the accretion disk. These outflows from the regions around supermassive black holes are actually a really big part of my research. I actually study what effects they then have on the surrounding galaxy. Now, these outflows are often detected in radio light. So if you spot a tidal disruption event, you make sure to look at it with telescopes across the entire spectrum of light. So almost so you can, track the evolution of the whole process of the shredding and then the spiraling down into the accretion disk and heating up and then starting to glow. And then this outflow that sort of regulates how fast the black hole can take in material that you then see in radio light. So you can really see the evolution of these tidal disruption events actually happening, usually over a few months or so. So tidal disruption events, nothing new. But what's weird about the one that's been reported on by Senders and collaborators, AT2018HYZ, is that the TDE happened back in 2018, and only 970 days later, 2.5 years, was an increase in radio brightness then seen, indicating that only then had this outflow switched on, which is weird because the outflows, they regulate this glut of matter, right? When there's too much that comes in from this tidal disruption event, that's when they switch on to be like, oh, let's relieve some of this pressure. But that happened 2.5 years ago. There's been no extra matter observed falling in, no extra tidal disruption event to kickstart, to need an outflow. So what is going on? There's a couple of possible different explanations for this sort of delay to the outflow, but it's not something we've ever seen before. So until we see more of these sort of delayed outflows post-tidal disruption event, I think only then will we truly be able to narrow down which one of these possible explanations it could be. One option is the outflow has always been there, but perhaps there was a very dense region around the center of the galaxy where the supermassive black hole was, essentially shrouding that outflow from view, and it's only when the outflow has traveled far enough it's been able to sort of punch through that dense shroud of either gas or dust so that we could see it. That's one possibility. Another option is that there was a delay in actually getting the material close enough to the black hole to need an accretion disk. So perhaps when the star was first disrupted, what happened was that it was actually pulled into a ring quite far out from the black hole, but still fast enough to cause it to, heat up and start to glow. So you get that initial burst of UV optical X-ray light that identifies it as a tidal disruption event. And then slowly over time, it's worked its way inwards to the point where it really starts to speed up and starts to spiral in towards the black hole at quite a large rate. And that's when you then need that outflow to regulate that sort of glut of matter of the accretion of the black hole. Or similarly, perhaps there was some phase or state change to the actual material in the accretion disk itself. Perhaps it suddenly just got very, very hotter and things got more turbulent, and that's why the outflow was needed. So I think there's definitely a lot of good ideas in there, but it all really comes back to the physics of how this accretion around black holes works. That again, there's still so much that we don't know in terms of on like the nitty gritty of what happens. So I think with this, as weird of a thing it is that we've actually seen, I think it'll actually teach us a lot more about how this accretion happens and how these outflows are launched as well. Alright, that's it for night sky news for this month. As always, if you snap any pictures of the night sky, send them my way over on social media because I'd always love to see them, as well as any space news stories that you might, like me to cover in a future episode. You can tag me in whatever posts you see as well. But until next time, everybody, happy stargazing. I wanna have snow on the beach. That's how I'm assuming Taylor Swift's new song goes. Don't know yet. It's out tomorrow, the album. Very excited. Along with why the orbit change was 25 times larger than was predicted. Lager. Oh, I've got the hiccups.